In this tutorial, we will take a quick look at SoftMC, which is an FPGA-based infrastructure for characterizing and studying DRAM chips. Let's start with a brief summary. SoftMC is an FPGA-based DRAM testing infrastructure. SoftMC lets us characterize, analyze, and understand DRAM cell behavior. It is a flexible and easy-to-use tool providing a C++ API for programming. An open-source version of SoftMC is available on GitHub. Because of its flexibility, SoftMC enables a wide range of studies that are not practical to do using existing CPUs. Before jumping into SoftMC, let me first provide some background on DRAM. Here I show a typical system with a CPU and a DRAM module that has several DRAM chips. Inside the DRAM chip, there are multiple subarrays which contain many DRAM cells organized as a two-dimensional array. A DRAM cell stores a single bit of information as electrical charge. In a subarray, the cells are vertically connected to sense amplifiers, which can read the data from the cells and update it if needed. A row of DRAM cells is called a DRAM row. Now, let's look at DRAM commands that the memory controller issues to read data from a particular DRAM cell. To perform an access, the memory controller first activates or opens a row by issuing an activate command. Activate causes the cells of the selected row to share their charge with the sense amplifiers. Based on the charge amount received, the sense amplifiers determine the value that each cell stores, and then they restore the charge of the cells back to its initial amount. After row activation, the memory controller issues a read command to the DRAM. With that command, the data is read from the corresponding sense amplifier and transferred over the memory bus to the CPU. Although the memory controller has received the data, it still needs to perform one more operation to prepare the DRAM for a future access to a different row. The memory controller issues a precharge command to close an open row. The precharge operation turns both the row and the sense amplifiers back to their initial states. This is basically how DRAM is accessed. In this slide, I would like to show the status of a DRAM cell and a sense amplifier prior to performing the key DRAM operations and on the completion of them. When the cell is not yet activated, in other words, when a row is closed, DRAM cells leak their charge gradually. The interval during which the data is retained correctly in a DRAM cell without accessing it is called retention time. DRAM cells are typically refreshed at 64 milliseconds refresh period to ensure DRAM stores the correct data continuously. Now let's look at how DRAM commands change the status of the DRAM cell and the sense amplifier. At the point where we just issue an activate command, the DRAM cell is fully charged and the sense amplifier is idle. After a specific time interval, which we call ready to access latency, the memory controller can issue a read or write command. Later, when the cell is fully restored after the activation latency, the memory controller is free to issue a precharge command to precharge the DRAM to access a new row. During the precharge operation, the sense amplifier gradually turns back into its idle state. We call the time associated with the precharge operation precharge latency. Let's go a bit deeper and understand more what these latencies mean. What if the memory controller does not obey these latencies? Can we reduce DRAM access latency that way? The memory controller issues the DRAM read command earlier in time, the DRAM will try to serve the data from a sense amplifier that may not have been properly sensed the data, which may lead to reading corrupted data. Similarly, if the memory controller issues the precharge command earlier, the DRAM will start precharging without fully restoring the cell, which may again result in read error during the next access to the cell. Last, if the memory controller does not wait for the precharge operation to complete and issues an activate command to a new row, then the activate operation will begin when the sense amplifier has some amount of charge, which means it is not completely in idle state. That may again result in reading incorrect data. So, reducing the timing intervals between the commands to improve DRAM performance may negatively affect DRAM reliability. To develop such mechanisms, the exact characteristics of real DRAM cells need to be studied. There are also other factors affecting DRAM reliability and latency, such as temperature, voltage, inter-cell interference, manufacturing process variation, retention time, and more. You can learn more about how these factors affect DRAM performance, reliability, and power consumption during this projects and seminars course. To design more reliable and faster DRAM, we need to better understand the effects of such factors. Many factors affecting DRAM reliability and latency cannot be properly modeled in simulation or analytically. To design, evaluate, and validate mechanisms that could improve reliability and performance, we need to characterize, analyze, and understand the behavior of real DRAM chips in terms of reliability and performance. And we can achieve this using SoftMC. In fact, there is a large body of past research that uses SoftMC to explore some aspects of DRAM behavior. However, there is still a lot to do in this area. Let's see an overview of SoftMC, see what the infrastructure looks like, and then write a simple DRAM test using SoftMC. SoftMC is an FPGA-based DRAM characterization infrastructure that has the ability to test any DRAM operation and any combination of DRAM operations with arbitrary timing parameters. This is all possible using the simple C++ programming interface that SoftMC provides. So users don't need to make changes in the FPGA application, but rather write DRAM tests completely in software. Let's see what the overall infrastructure looks like. This is a version of SoftMC running on an FPGA board that has DDR3 module slots. The FPGA is programmed with a SoftMC bit file, and the DRAM under test is plugged into the FPGA board. The FPGA board communicates with a standard desktop machine via PCIe. Since DRAM operation is sensitive to temperature, we have built a heating system consisting of a heat chamber, a heater, and a temperature controller. This enables us to control the temperature of the DRAM chips. On the right-hand side, you see SoftMC running on a more recent FPGA board that has DDR4 slots. In this setup, instead of a heat chamber, we use rubber heaters on both sides of a DDR4 module to control DRAM chip temperature more precisely. The rest of the setup is similar to the setup on the left-hand side. In the second part of the tutorial, I will demonstrate how a simple DRAM retention profiler can be developed using the DDR4 version of SoftMC. In this demo, I will show you how to use SoftMC to write a simple retention profiler that profiles the retention time of a single DRAM row. Here in this project directory, we have two files. One which I named retention_demo.cpp. So here for now, we just have the main function. And I also created a simple makefile that will just build this C++ file. There's nothing special. It just includes some libraries and headers that are needed to compile a SoftMC program. I'm now working on a machine that has FPGA connected to it through the PCI Express bus. And that FPGA has already the SoftMC hardware loaded into it. We start writing every SoftMC program by first defining a SoftMC platform. In the SoftMC API, there is a SoftMC platform class, and we just create an object of it. So here we got an error because we need to include the corresponding library, the corresponding header files. So here, this is already in the include path, but the header in the SoftMC API is called platform.h. Okay, so we have that included. So here we just create an object of the platform, but we need to initialize it. So we just basically this piece of code shows how to initialize the SoftMC platform. All we do is calling the init function and then checking if it returned the success code. And here we are also printing an error message in case something went wrong. In order to get rid of this error here, I will just add the IO stream header. Okay, after initializing the platform, we are pretty much ready to write SoftMC programs, but there are two things that that is also good to do. So the first thing is calling this reset FPGA function of the platform object. This will basically raise the reset signal in the FPGA that will just reset like all the SoftMC state. The second thing we will do here is we will call the set_aref function, which is enabling or disabling the auto refresh. So the SoftMC hardware implements a auto refresh mechanism, which basically automatically issues DRAM refresh commands. So here for this particular experiment, we don't want SoftMC to issue refreshes to DRAM under the hood. because we are going to look at the retention time of the cells, right? So we don't want to refresh those cells. And basically, we simply disable the refresh by calling this function. The goal of this experiment, as I mentioned, is to find the retention time of one particular DRAM row. We will try to achieve this goal by first testing the DRAM row with a certain retention time value, and then if we do not observe any retention failures at that retention time, we will keep increasing the retention time and continue testing the row until we find the retention failure. The output of the experiment will be the retention time in milliseconds, or the smallest retention time in milliseconds that leads to retention failure for the DRAM row that we are testing. And now we have everything ready. We can start writing our first SoftMC program. So how we write SoftMC program, or how we program SoftMC in general, is just very similar to sort of like programming any other device connected to your system. So it has its own, so SoftMC in the FPGA has a very simple processor that implements a very limited set of instructions. So in this tutorial, or in this demo, we will go over some of those instructions. But basically the general flow will be like you creating a SoftMC program and then inserting some instructions to it and letting that program execute on the SoftMC. As I mentioned, in this experiment, we want to profile one row from one particular bank. So for that, let's here define first the bank ID that we want to test. I will just pick bank 2. In DDR4, there are either 8 or 16 banks, depending on the module. And let's also pick a row that we want to test. So the row IDs are like either, so they're like in a single bank in DDR4, there are either 32K or 64K rows. So you can basically pick any number from 0 to 32 or 64K. So you need to basically know how many rows the module you are testing has. So here I will just like pick row 1000. Okay, and step 1 in this experiment will be initializing some data. So in order to be able to test retention time of a DRAM row, we will first need to put some data in there, that data that we know, and then wait for the retention time to let the cells leak some charge. That may lead to losing the data that we just written to it, right? And then read the data back and then check if it is still the data that we wrote to the DRAM cells, or whether the data changed because of the retention failures. Okay, so step 1 is then initializing data in the target row. So actually, let's not call this step 1 because there are some other sub-steps that we will need to do. Let's do it this way. So let's call this step 0 first, and step 0 will be to create a SoftMC program. So there is a program class that SoftMC API defines, and then we will create a instance of it, which we just call a demo prog. So this will probably complain. We need to add the program header over here. Let me just quickly do that over there. Okay, so now we have this object over here. We can start putting instructions into this program. So step 1 will be to pre-charge all banks. So here the reason we are doing this is just in case there is some DRAM bank that is left open prior to starting this experiment. It can be basically an earlier experiment that finished without pre-charging all the banks. Basically, we want to avoid making the mistake of activating a row while there is already a row active in the bank. So in order to make sure that there is no active row in any of the banks, we basically issue a command that will pre-charge all the banks at once. So in DDR4, there are 2 different pre-charge commands. One of them, it's usually like written like this for short, like precharge. This stands for precharge all, and then there is also the precharge command, which is shortened like this, and this will precharge only one bank. So here we will issue an instruction or a DRAM command that will precharge all banks. We insert an instruction to a SoftMC program by calling the add branch by calling the add instruction function. So this takes an instruction as an argument. The DRAM command that we want to issue is is SMC underscore precharge. So this will this instruction will basically result in issuing a precharge command to the DRAM. But so here one thing you will need to notice is that this is returning a min instruction, but add instruction is taking an instruction object. So those are basically two different types of instructions that we have in the SoftMC API. Let me quickly explain you the difference. So there is min-inst and there is inst. So basically, inst is all instructions that are executed directly in the FPGA logic. So those instructions have nothing to do with DDR4. So those are basically instructions such as load immediate, add, or subtract, or branch. So yeah, but on the other hand, min instructions are instructions that basically result in DRAM commands. So just as an example, like activate, precharge, read, and write. And the reason we have two different sets of instructions over here is because since FPGA logic is not designed to achieve, or it cannot work at very high frequencies, but we want to be able to use the DRAM with very high throughput, so we can like achieve like much better like bandwidth when we access it. So we want to operate the DRAM at very high frequency, and and here the trick is that we operate FPGA logic slower, let's say at F frequency, and then we operate the DRAM bus at 4F frequency. And then how this works is at each FPGA cycle, the FPGA can, but doesn't have to necessarily issue 4 DDR4 commands in a single cycle. So basically, at every cycle, there are 4 DDR command slots in the FPGA logic that are issued back to back within a single FPGA cycle. And this is why basically we have 4 different instructions here. This is why we have 2 different types of instructions. Min instructions are basically 4 min instructions can be packed together to create one instruction. Okay, so here our goal is to issue a precharge operation, a precharge command to issue all banks at once. So we'll need to put this or create an instruction out of this. That we can do by putting it inside this function called pack min instructions. So this will take 4 different min instructions and create one instruction. So in this cycle, we just want to issue one precharge command, and the rest will be, so let me do this way, and the rest will be 3 knobs, right? Okay, this is what we want to do. So, so the first slot will get the precharge command, and the next 3 slots will not. I forgot a parenthesis over here, and the next 3 instructions will do nothing basically. Okay, so let's finish this SMC underscore pre function. So this is taking 3 parameters. First of them is the bank address register. So this is not the bank ID that we have defined here, but this is an ID of a SoftMC register. So like if you are familiar with instruction set architecture such as x86 or RISC-V or MIPS or any other instruction set architecture, so they have some general purpose registers, right? So SoftMC also has its own registers. And then what all those different SoftMC instructions take as arguments are those those register IDs. So here we will need to pass a register ID. So let's define it. So here below step 0, I will make a sort of a section here to allocate SoftMC registers. Here, there's like nothing fancy about like allocating those registers. We will just basically assign some numbers to them, and or we will assign some names to numbers. So let's define let's allocate a register for the bank ID, and let's assign it to 3. So basically, the third SoftMC register here we will use for the bank ID. Just a bit of information. There are in total 16 SoftMC registers, but you can use only a register from 3 to 15 in your programs as like general purpose registers. There are 3 more registers, register 0 to 2, but those are reserved for a special purpose. We will use one of them later in the program. Okay, so here we picked register number 3 to use as a bank ID register. Okay, so here we can just pass this register over here. And the second argument is here defined as increment bar. So this is to increment the bank ID register. So this is an option in case you want to, just like in the later instructions in the program, use an incremented value of this bank ID. So it has some uses. So this is why we implemented the API this way. But right now, we don't want to increment the bank ID. We want it to stay at its like value, which we did not set yet, but we will set shortly. And the third argument here is whether we want to precharge all banks or precharge only one bank. So in this case, we wanted to precharge all banks because that's what we defined as step 1. And then this is why I will say this just as 1. But if this was 0, only the bank specified by this register would have been precharged. So basically here, because we set 1, it doesn't matter really what is the value of this register. In fact, we didn't set it yet. So even if he did not set it correctly here, this instruction should work because it will just ignore this value over here and precharge all banks at once. But let's now initialize this register over here because we will later use it. So let's insert another instruction. So this instruction that we will insert is from type 1, right? So this is an FPGA instruction. It's not a DRAM instruction, so we can directly pass it to the add instruction function. We don't need to pack it. And this takes 2 arguments. One of them is the immediate value that we want to load into the register. So this will be bank ID, and the register we want to use for this will be register bank ID. Okay, so this is basically the instruction that we will need to issue in order to initialize the data in this register. To finish step 1, we need to do one more thing. So recall from the slides that DRAM commands are associated with different timing parameters. In order to complete precharge correctly, we will need to wait for the precharge latency. So here, let's define it as TRP. So this is also how it's defined in the DRAM datasheet. So like precharge latency, for short, it will be TRP. So let's define it in cycles. So I looked up the module that I'm using, and in its datasheet, TRP is defined as 15 nanoseconds. So here I will divide it by the DDR4 period. This is the period of like the clock period of the DDR4 bus that we are using in the FPGA, and then we will round this up. So like we make sure that we wait for 15 nanoseconds or slightly more than that, depending on what is the result of this division, right? So we basically, if the datasheet says defines 15 nanoseconds as precharge latency, we need to make sure we wait for at least 15 nanoseconds, but it is fine if we wait for more than that. Okay, so let's define this DDR4 period over here. So here, this is the 1.5 roughly is the DDR4 period of the FPGA we are using. And also, let's get rid of this error here by adding the corresponding header file. Okay, now we have defined TRP here. Let's make sure that after issuing this precharge instruction, we will wait for at least TRP cycles. So here, since we packed 3 knobs over here, we have already waited for 3 cycles. All we need to wait for is TRP minus 3. Here I will introduce sort of a helper instruction to make this easy. And so I will call it add knobs. and we will pass the current program that we are using and the amount of cycles we would like to just wait, right? And okay, so let's define this function. Okay, now let's define this add knobs function. So I will just add it here, and it will be defined like this. So it takes the program and the count, as I said, and then what it does is it basically inserts to the program one or more packs of 4 knobs, right? So here the thing is that this will, so if the count is 1, this function will insert 4 knobs. So this is not ideal if you want to ensure precise timing in your program. But for simplicity, we will just keep it like this. Okay, now let's get into step 2 of initializing data in the target row. So step 2 will be activating that row. Activate the In this step, we will issue an activate command to activate the target row. First, similar to what we did here with the bank ID, let's also allocate a register for the row ID. And let's just use register number 4 for that. I will just move this here so we have all register allocations in one place. So now we have the register allocated. Let's also initialize it. We basically do it similar to how we initialize the bank ID. We initialize the register row ID to the row ID value that we defined over here as 1000. The next thing we will do is adding an activate instruction to the program. And this is the line to achieve that. So this line is very similar to this line over here, where we issue the precharge all command. But instead of precharge all, we change this to SMC act, which stands for activate. And then we pass the bank ID and register row ID. And those zeros over here indicate whether we want to increment the bank ID or row ID. We don't want to increment on any of them right now. And here again, we packed this mini instruction to an instruction with some knobs over here. So there is also a latency associated with activate, as we see in the slides. It's the ready to access latency, or as it is defined in the DRAM specification, TRCD. So TRCD for this module, I looked it up, was 15 nanoseconds, and we just divided by the DDR4 period as we did here to find the TRCD cycles. And similar to what we did here, we will just insert some knobs. Now, like after this instruction executes, and then we wait for some cycles, we ensure that the row has been opened successfully. Now let's get into step 3, which is the performing the actual writes to the DRAM row. So before issuing the DRAM write commands, we first to decide what data we want to write to the DRAM. So for that, here I will specify step 3.1. And then in this step 3.1, we will set up the data that we want to write to the DRAM. So in SoftMC, all instructions, let me write it up here, all SoftMC instructions are 64-bit wide. So like they're encoded using 64 bits basically. Yeah, so for that reason, we cannot pass like all the data that we want to write to one DRAM row, which is 8 kilobyte in size. DRAM row size is 8 kilobytes. How we do it in SoftMC, how we write like arbitrary data to 8 kilobyte a row is by using a special register that is like not part of the registers addressable over here, like when we allocate, but it's accessible with a special function. So let me describe you that. So here in this piece of code, we first allocate another register. So for some reason here we picked register index 10 for it. Actually, let's change that. Let's go in order and then make this 5. So we call this register register input data. And here we initialize like a bunch of f's to it, which means just like all ones, right? So here in this experiment, we will write just once to all cells in the entire DRAM row. So this is just a general purpose register that we have allocated, and then we put ones to it. So this is a 32-bit register. So all general purpose SoftMC registers are 32 bits. Instructions are 64-bit wide. And yeah, so once we have this like all ones in this register, then we can access the write register, which is 64 bytes. So this, let me write it here, write register is 64 bytes. And then we use this SMC underscore LD or load write register function to access different portions of this very wide register, right? And then here we basically create a simple loop. There are 16 4-byte chunks basically in 64 bytes, and initialize all portions of this write register with all ones. And this write register is what SoftMC uses to when sending data to the DRAM when write commands are issued. Now step 3.2 will be writing to every column in DRAM. So every write command will access one column for DRAM, and then one column basically, or write one DRAM command will basically write 64 bytes to the DRAM row. Let's first allocate some more registers that we will use for this. So here we have allocated register for the column ID and register for the total number of columns we have in this DRAM module. So I will move those register allocations up here. And in these two lines, we initialize these two registers. So we first want to write to the first column ID and then later write to other column IDs. And the total number of columns we have are 128. But because of how column addressing works at DRAM command level, we multiply this by 8. So this is basically because after we perform a write operation using column ID 0, the next column will be located at column ID 8. Okay, so we always like go through columns by increments of 8. This is how just addressing works at DRAM command level. Here, basically, we have two options to perform 128 writes to the DRAM. We can create a C++ loop like we did over here, and then insert a bunch of write instructions, but that will unnecessarily insert too many instructions to the program. SoftMC is implemented on FPGA, and there's limited space, so the program size is also limited. And in order to keep the program size as small as possible, it is a good practice to use SoftMC loops. So for that, in order to be able to create loops in SoftMC, we added branch instructions to the API. So I will show you now how to create loops in SoftMC programs. So we have two instructions that we use for that. So first we need to add a label. So this is basically the point to which we can later jump in the program. So let's just name this as write loop, and also call another function which is add branch. Is there? I think I forgot this. Also add call the add branch function. This takes a bunch of parameters. So first of them is the branch type. There are multiple branch types defined in the API. We will use the branchless option, which I'll explain how it works now. So here the next parameter will be register not bank ID. So this should be column ID, and then register number of columns. So basically with this branch type over here, which is branchless, this branch will be taken while this register is smaller than this register over here. So in this part of the experiment, basically what we will get is this loop will repeat 128 times, right? So once for every column, as long as we increment the register, the column ID register by 8. And then last parameter here we need to specify is where we want to jump when the branch is taken, and then it will be just right loop, the label that we have defined over here. And then this is basically how we form loops. And then now let's put here the instruction that we want to perform in the body of this loop. And this is again similar to this DRAM command over here, to the activate DRAM command. We perform an SMC write at the first slot of the 4 DRAM commands, and then we pass the bank ID and the column ID. Here we don't need the row ID because it's obvious which row is activated. There can be only at most one row active in a bank. And this time we set 1 over here because we want to increment the column ID by 1. So we can also like set 0 here and then put another instruction below to increment this register, but it is just more work, and then it will result in slightly slower program because then we will spend an additional FPGA cycle to increment this register. But when we do it this way, this register will be incremented at the same time while we perform the write. Okay, and these two parameters, I'm not going to mention them now, but they are just to perform the write operation with some like different configuration. Okay, so this is basically how we write to the entire row in the DRAM. One thing I forgot to mention is by how much we increment this register when we set 1 here. So this is controlled with the special purpose or reserved registers that I mentioned over here. The first register, register 0, is basically used to specify by how much the column ID will be implemented. So we want to increment the column ID here by 8 because this is how column addressing works in DDR4. And for that purpose, I will add this instruction over here. So this will initialize 8 to register 0. So here I did not define I did not specify a name for this register 0 as we did for the column ID register, for example. Instead, we just give the index here as 0. Okay, now we have written data to the DRAM row. It is time to precharge this row so it has a chance to leak data. So when row remains active, it will never leak its data. So we have to precharge it and then wait for some retention time. So step 4 is to precharge the row, and then we do it in a very similar way as we did here. Where is it? Okay, here. So we issue this precharge command. So now we don't necessarily want to precharge all banks in the DRAM, although we can because we did not activate another DRAM or we do not use any other DRAMs. They are already precharged. So this can remain as 1. There will be nothing wrong in the program, but I will just change this to 0 to only send a command that will precharge this particular bank here defined by the register bank ID. Okay, and similar to what we did over here, we will need to wait for the precharge latency. Okay, now we are almost done with this part. One last instruction we need to add to this program is SMC end, which specifies the end of the program. And then we can run this program by just calling the execute function of the platform and then providing this demo proc as an argument. So this function call will download this program to the FPGA, and then the FPGA will start executing this program right away. Okay, so if you run this program will just write to the entire DRAM row and exit. But in this test over here, our goal is to test the retention time of one particular row by increasing the retention time. So this will require writing to the same row multiple times. For example, when we test with 64 millisecond retention time, let's say, and we do not observe any retention failures, we will need to repeat the experiment with some higher retention time value. So since we will repeat this like multiple times, let's put this inside a function that we will simply call here from the main. Let's call this function initialize data. Initialize data, and we will need to pass the platform object, and also the bank ID and the row ID. And then we will copy all the lines over here, starting from the program creation to the new function. So let's define it over here. It will be initialize data. Let's set the parameters later. So these are all the lines that we need. And these are the parameters this function gets. And from the main, we will simply call this function as we need, and it will initialize data to the DRAM. And the next step, I think this is step 5, is to wait for the specified retention time that we want to test with. So let's define that first. I will put this here as current retention time, and let's start from 64 milliseconds. So this is the default refresh period in typical DRAM modules. We will wait for the specified retention time by simply making the thread sleep. Basically, this step 5 has nothing to do with SoftMC, and there are multiple ways to make a thread wait. But here, in this example, I will use a function that I'm using in other SoftMC experiments. So we will call it wait for retention time, and then it takes as an argument the amount of time we want to wait. And let's define it over here. So this is just using the chrono library from like the standard C, and it just waits for the specified amount of time. I won't go into detail for this, but it's basically making the thread sleep for the for the amount of like milliseconds you specify over here. This will require the chrono header. Let me add it here quickly before it complains. Okay, and then basically this is all we need to do in step 5, just wait. And in step 6, we will need to read some data back from the DRAM. And for that purpose, we will need to issue DRAM read commands. Issuing DRAM read commands will be very similar to issuing write commands. So let's also define quickly a function for that. Let's call it read data, and its arguments will be exactly the same as in here. So as I said, this will be a function or a program that will be very similar to initialize data. So let's let's write it by copying this initialize data function and changing some parts of it. So its name will change, obviously. So this will be read data. And then we won't change much. So maybe we can change some of the comments. So instead of write, this will be read. We won't need step 3.1, where we initialize the write register, because we won't use it when performing reads. So I can just get rid of this. And maybe step 3.2 is also not relevant there. I mean, that comment is not relevant. And so this will be also write, and then this is reads. We may also change this label over here, although we don't need to. And then I guess the last thing we will need to change is this command over here from write. We will change it to read, and then hopefully, let me check. Yes, this seems correct. So this basically is the same thing as writing, right? So the only thing we changed here is the command. So we still need to activate a row in order to perform a read. And then similar to writes, we need to wait for TRCD, for the ready to access latency, in order to issue the first read command. And then after we are done with that, we pre-charge the bank. And yeah, we are done with reading all the data in the row. So this step 6 over here, running this function, will read the data from DRAM, but it won't give it to this C program over here. So to get it to a data buffer here in this program, we will need to do one more step, which is receiving data from the PCIe. To get the data read from DRAM over PCIe, we simply need to call the receive data function of the platform. This takes 2 parameters. One of them is the like target buffer that we will ask this function to write the data. So let's define that first. I will define it as an integer array. Every integer is 4 bytes. So let's call this buff. every integer is 4 bytes and a DRAM row is 8 kilobytes in size. So then we will need 8K divided by 4 number of integers to store all the data of a DRAM row. And basically the first parameter of this receive data function is the buffer, and the second one is the number of bytes we want to read. So here, I think this parameter is named as number of words, but that's incorrect. So it's really the number of bytes we want to read. So here it will be 8K again, which stands for 8K bytes or 8 kilobytes. Okay, and then after running this function, after reading the data, we will have this buffer over here populated with the data that was read from the DRAM. And the last step will be to check for retention failures. In this step, we will basically iterate over all elements in this buffer that we have defined, and then check if they contain any retention failures. And we do that with this piece of code over here. We'll loop through all elements and check if their value is all ones. So you can represent all ones with like as a hex number as we did above, or just using black -1. So this will result in the same thing. But let's also put like Fs over here, so it's consistent. Okay, so we check every element if it's all ones. If that's not the case, if there's like at least one bit that is 0, then the program will print this message over here and exit. And the message is the bank ID and then the row ID. And it says that this bank and row ID cannot retain data correctly for whatever this retention time is in the test, milliseconds or more. So in this experiment, we want to test different retention times in case the first retention time we specified here does not find any retention failures. Right? So for that purpose, let's wrap this inside a infinite while loop. So I will just do it like this. Okay, so like this will keep iterating forever or until it returns from here. Let's also put return 0 over here. And then after we complete one iteration of this loop, we would like to increment this current retention time. Actually, we need to move the current retention time definition over here outside the loop. And then we will increment it at the end of each iteration. Let's increment it by 64. It seems this is like all we need to do, if I'm not missing anything. And now let's compile this program and then see if it works. We can just compile by running make. And if everything is correct in the program, it just should successfully compile. Yes, it did. And then we can see that it created a SoftMC, it created a binary file here. So before actually running it, I would like to here write one more line. I would like to add one more line that will print this message. So it will print the retention time that we are testing with in this iteration. Okay, so let's compile this again. We forgot to save the file. Let's compile this again now. Okay, and then now we can run the program. We run it with sudo because SoftMC accesses some device drivers and it requires this program to be served with sudo. Okay, we have started it, and so far we see that we did not come across a retention failure. Therefore, standard specifies refresh period of 64 milliseconds, but that does not mean that cells will fail after 64 milliseconds necessarily. In fact, this is really the worst case retention period of the cells in the DRAM chips, and it depends on many things. It depends on data patterns that you write to DRAM. It also depends on temperature. So the current device or the current test here is running on a DRAM module that is heated up to 50 degrees Celsius. And basically, if it was like, if the temperature was set to higher value, we would, in that case, expect shorter retention time. But here we see that this row does not have any cells that fail below, well, almost 3 seconds so far. So they can retain data for quite a long time, at least at this temperature. So I will cut the video here a little bit, and I will come back when the test finishes. The experiment has finished, and here from the output we can see that this particular row cannot retain data for more than roughly 7.6 seconds. In this demo, we use SoftMC to write a simple DRAM retention profiler that finds the retention time of a single DRAM row.